Okay, now in this video I want to go through the derivative of the exponential function. So the exponential function is we have y equals e to the power x. And if you haven't come across this exponential function until now, the e here just stands for a number. E is equal to the number, or is approximately equal to 2.718, and it just keeps going. In the same way, you might think of pi is approximately equal to 3.141, and it goes on. We usually approximate it by 3.142. So in the same way, e just stands for a number. So what we have is a function where y is equal to some number raised to the power of x. But in the same way that you almost always write pi as the symbol pi and not 3.142, we always write this number 2.718 as e. And I won't go into how we get this, why this number is special. It has some very special properties, one of which we will see now. But just so that you understand, this is quite different to a polynomial, because all the functions we looked at so far, at least for differentiation, we had functions like, say, x cubed plus 2x, say, to the power 4, and we differentiated that. In this case, the power is always a constant, whereas in this case, my base is the constant, and my power is a variable. So in this case, the power is x, which is a variable. Now, y equals e to the power x, with the derivative of y e to the power x, that's dy over dx, is also equal to e to the power x. So what this says is that if I have the function y equals e to the power x, where e is just this number raised to the power of x, then the derivative is also equal to that same function. So this is quite interesting, because when in the case of polynomials, if we keep differentiating, we will eventually get down to 0. But whereas in this function, you can take the second derivative, the third derivative, and so on, and you always get e to the power x. And there are many proofs to show that the derivative of e to the power x is also e to the power x, but I won't go into that in this video. But let's just use the fact that the derivative of e to the power x is equal to e to the power x to do more derivatives involving this number e. So let's say we have a function y equals e to the power 2x plus 5. Now to differentiate this, I can use the chain rule, because I have e is some function and I have raised it to a power of another function. So here I have a function of a function. So in this case, I can use the chain rule. So if you remember from previous videos, when we had, say, y equals, say, some function, say 2x plus 5 raised to a constant, we said let's take this, whatever is inside the bracket, as my t substitution. In this case, what I'm going to do is I'm going to take my power as my t substitution. So let's say let t equals to 2x plus 5. If t is equal to 2x plus 5, then y would be equal to e to the power t. Okay, then we take these derivatives. So let's take dt over dx, which is equal to 2, and dy over dt will be equal to e to the power t. Because if the derivative of e to the power x with respect to x is just e to the power x, then the derivative of e to the power t with respect to t should be equal to e to the power t. And then we just use the chain rule, which says that dy over dx is equal to dy over, let's write dx there, so we have dy over dt times dt over dx. Now dy over dt is just e to the power t, and then I have times dt over dx, which is equal to 2. So and my final step would be to substitute back for t. So I took the substitution, t equals 2x plus 5. So I'll bring this 2 to the front, so I can write this as 2 times e to the power 2x plus 5. And that would be the derivative of this function, y equals e to the power 2x plus 5. Okay, let's take a few more examples of this function. So let's say I have another function, y equals e to the power, let's say, 2x squared plus 6x. Once again, I can take my power as my t substitution. So I can take t equals 2x squared plus 6x, which means y would be equal to e to the power t. Then dt over dx will be equal to, differentiating this function, I get 4x plus 6 dy over dt will be equal to e to the power t. And then I use the chain rule. So the chain rule says dy over dx is equal to dy over dt times dt over dx. And that's just the chain rule. Then I substitute for dy over dt, which is equal to e to the power t, times dt over dx. So dt over dx is equal to 4x plus 6. And if I substitute back for t, I get e to the power 2x squared plus 6x times 4x plus 6. Now just from these two examples, you may have seen a little pattern. And in the previous chain rule videos, I showed some shortcuts to deal with functions like y equals some function raised to the power of a constant. So in this case, let's see what we can derive for e raised to the some function. So if I have, let's say, y equals e to the power of some function in x. Now, if y equals e to the power of some function, let's say let t equal to whatever that function is. So that's what we did in the previous examples. I had y equals e to the power of some function in x, and I took t as that substitution, whatever the power was. So in this case, let's say let t equals fx, and so in that case, y would be equal to e to the power t. So differentiating, I get dt over dx will be equal to, and I'll write this as f prime of x. I don't know what this function fx is, but its derivative can be written as f prime of x. Then dy over dt will be equal to e to the power t. And then using the chain rule again, I have dy over dx equals dy over dt, which is equal to e to the power t, times dt over dx, which is equal to the f prime of x. Now t is equal to fx, so I get e to the power fx times f dash of x. So this would be the derivative of e to the power fx. Now if you didn't understand the derivation of it, at least you'll be able to recognize this function here. So this is dy over dx. I'd say this is the most important bit here. So what it says is if I have e raised to some function, then the derivative is equal to e to the power of that same function times the derivative of whatever that function is. So if we try and use this rule, what we just derived, to find, let's say we have function y equals e to the power, let's say 2x squared plus 6x cubed. Now it says if I have y equals e to the power some function, then write down dy over dx. You can use a t substitution again, but to do it in one step, what you can do is you can say e to the power of the same function. So I write this same function down here. So I have e to the power 2x squared plus 6x cubed. But then I got to multiply that by the derivative of whatever that function is. So the derivative of this power. So the derivative of 2x squared, that's 4x. Then I got plus the derivative of 6x cubed will be 18x squared. So this would be dy over dx for this function.